is a walkthrough of problem 3 on exam 2 in module 1, which is on page 24 in the book Problem Solving Guide for Electromagnetism and Optics, 3rd edition. Problem 3 is a point charge of minus 3 nanocoulombs is located at 2 centimeters 1 centimeter, and a point charge of plus 5 nanocoulombs is located at minus 1 centimeter minus 1 centimeter. Part A, what is the magnitude of the electric field at the point 5 centimeters 5 centimeters? Part B, an electron is placed at the point 5 centimeters 5 centimeters and released. What is its acceleration? Give the magnitude and direction. Part C, where could an electron be placed so that it would experience no electric force? Give the coordinates of the point. So part A, what is the electric field at the point 5 centimeters 5 centimeters? Let's start with a good diagram. There's a nice grid. We have a negative 3 nanocoulomb charge at the point 2 centimeters 1 centimeter, which is right here. We have a plus 5 nanocoulomb charge at minus 1 plus 1. That's right here. The convention I like to use is positive charges are dark and negative charges are hollow, and the bigger the charge, the bigger the circle. Just as a reminder, just so I can keep track of which charge is which. We want to know the electric field way over here, 5 centimeters, 5 centimeters. What's the field at this point? Let's sketch the electric field vectors. This is a negative charge, minus 3 nanocoulombs. It's closer than this one. It's going to produce a field towards it because it's negative. So we can just put a line here, represent that electric field vector. This is a positive charge. It's further away, but it's bigger. It's going to produce a field away, something like that. So right away we know the electric field is something small. These two are almost in opposite directions and probably downward, something like that. To get the magnitude of these vectors, we need the distances. How far is this charge away from that point? How far is this charge away from that point? We can use the Pythagorean theorem to get those numbers. The distance, the 3 nanocoulomb charge, is 3 centimeters in the x direction, 4 centimeters in the y direction. So the distance is 5 centimeters. We can put that on the diagram. The 5 nanocoulomb charge is 6 centimeters away in the x direction, 4 centimeters away in the y direction. Again, the Pythagorean theorem gives us the hypotenuse, which is 7.211 centimeters. So now we have the distances, we have the charges, we can get the magnitudes of the fields. The magnitude of the electric field from the 3 nanocoulomb charge is 10,790 newtons per coulomb. In this direction right here, we converted everything to SI units. It's 3 times 10 to the minus 9th coulombs, and 0.05 meters is the distance. For the 5 nanocoulomb charge over here, the magnitude is 8,640, and that's away from the charge. So now we have the magnitudes of the two vectors. To add them, we need the components. To get the components, we need the direction. So we can use the arctangent function. To start, let's define some angles. We'll call this angle theta 3, theta for the 3 nanocoulomb charge. This angle theta 5, theta for the 5 nanocoulomb charge, the angles they make with the horizontal axis. So the arctangent of angle 3 is 4 centimeters divided by 3 centimeters. That angle is 53.13 degrees. Theta 3 is 53.13 degrees. Now theta 5, it's the arctangent of 4, the opposite side, divided by 6. The arctangent of 2/3, which is 33.69 degrees. So now we can go up here. This angle, theta 3, is the same as this angle. And then theta 5 is this angle right here, so that's 33.69 degrees. So now we have the angles the vectors make with the horizontal. With the angles, we can get the horizontal and vertical components of each of the two vectors. We'll start with the field from the minus 3 nanocoulomb charge, which is this vector right here. Remember, it was 10,790. The x component is minus 10,790 cosine 53.13 degrees. That's this direction right here. The y component is the magnitude times sine 53.13 degrees. That's this component right here. They're both negative. That's minus 6470. That's minus 8360. Now we'll get the field from the plus 5, which is at 33.69 degrees. The magnitude is 8,640. 8,640 times cosine 33.69 will give the horizontal component, which is 7190. 8640 times sine 33.69 will give the vertical component, which is 4790. That's this right here. So focusing on only the fields, we started with this situation. We got the magnitudes, we got the angles, we got the components. These two are the components of this vector, and these two are the components of that vector. So now hopefully you can see that they're much easier to combine. In the x direction, we have 7190 positive and 6470 negative. The resultant is 720 positive. In the y direction, we have 4790 up, 8630 down. That is 3840 down. So we started with this, we got to this, and now we have this. The net in the x is 720. The net in the y is minus 3840. Now we're almost done because we have the components. We can get the magnitude. It's e sub x squared plus e sub y squared, square root. So the magnitude, the net electric field vector at the point 55 is 3910 newtons per coulomb, and it is 79.4 degrees below the horizontal. So we have the direction, we have the magnitude, and that's the answer. That's the electric field vector at 5,5. And we can put it on the diagram. That's about where we thought it was. If you remember the very beginning slide, we said it's a small vector, it's down somewhere in this direction. Let's go back to the original diagram and see. The two electric field vectors that we drew are this. That one's 10,790. That one's 8640. And we guessed that it was going to be something like that. And it looks like we were right. If you try to add these head to tail, you can take this vector and stick it over here. Looks like the tip is going to be somewhere in that region. We should be happy. Looks right. This was just part A to this problem. We got a long way to go. This is the hardest part of this problem, though. Before we get to part B, let's review our path. This was a multiple step problem. First thing we did was we drew a good diagram. Let's start with a good diagram. Put the charges in the right place. Then we drew the electric field vectors so we can see the direction. We got the distances from the electric charges to the point at which we're measuring the field. Then we got the magnitudes of the vectors. How big are they? KQ over R squared. 10,790, 8,640. Then we got the directions. We got the angles using the arctangent function. With the angles and the magnitudes, we can get the components. So now it looks like this. We sum the horizontal and vertical components, and we get this. Now we use the Pythagorean theorem to get the magnitude and the direction of the electric field vector, which we get with arctangent function. So 3910 newtons per coulomb at 79 degrees below the positive x-axis, and we can sketch that in. Okay, part B. An electron is placed at this point and released. What is its acceleration? The electron is negative, it's going to accelerate opposite of the field. So the electron is going to go that way. The direction of the electric field is the way a positive charge would accelerate. Now, we did all that work to get the field. Let's use it. F is QE. We don't have to go Q1, Q2, add the vectors, get the direction, blah, blah, blah. We got the E. So all we have to do is plug in the Q, the charge on the electron. If we plug it in, 1.6 times 10 to the minus 19th coulombs, there's the field. The force is 6.26 times 10 to the minus 16th newtons at 79.4 degrees above the negative x-axis. It's in the opposite direction. That way. We have to get the acceleration. Yes, the force is small, but the electron has such a small mass, the acceleration is going to be huge. The mass of the electron is 9.11 times 10 to the minus 31st kilograms. And there's the force. We can solve for the acceleration. We get 6.9 times 10 to the 14th meters per second squared. That is quick. 6.9 times 10 to the 14th meters per second squared at 79.4 degrees above the negative x-axis. Let's sketch it in. And let's use a different color vector so we don't think it's an electric field vector or a force vector. That's an acceleration vector. And it's 6.9 times 10 to the 14th meters per second squared. That's the answer to part B. On to part C. Where could an electron be placed so it would experience no electric force? The only way it's going to experience no electric force is if the field is zero. Where can the field be zero? Not between them. If I stick a charge here, positive or negative, it's going to accelerate. If it's positive, it's going to go to the right. If it's negative, it's going to go to the left. The forces, the fields in between the two charges are in the same direction. A positive charge would get pushed by this positive charge and pulled by this negative charge. It would accelerate to the right. A negative charge would get pulled by the positive charge and pushed by the negative charge. It would go to the left. The field can't be zero between them. It can't be zero over here because the positive charge is bigger and closer. It's always going to win that tug of war. It can only be zero somewhere over here. This is a smaller charge, but it's closer. So let's define the distance from this charge in the horizontal direction as x. And let's put it on the diagram. Somewhere out there. To the right of the minus 3 nanocoulomb charge is a point where the electric field is zero. Now we can write the expressions for the two contributions to the field from each of the 2 point charges. E is kq over r squared. The minus 3 nanocoulomb charge produces a field of kq over r squared, and r is just the distance x that we defined. The 5 nanocoulomb charge is further away. It's 3 centimeters further away. So the field produced by this charge, the 5 nanocoulomb charge, at the point in question, way over here, is kq over r squared. The q is 5 nanocoulombs. The distance away is x plus 3 centimeters. When these fields are equal, the field is zero because we know the fields are in opposite directions out there. So let's set them equal. The magnitudes of the field are the same. Here's the field from the 3 at x. Here's the field from the 5 at x plus 3 centimeters away. The same point. Out here somewhere. We can cancel the k's and cancel the nanocoulombs. Now we have 3 over x squared is 5 over x plus 3 squared. Cross multiply, take the square root. We have the square root of 3 times x plus 3 centimeters is square root of 5 times x. We can distribute the square root of 3 in there. We can subtract square root of 3x from both sides. We can factor out the x, divide both sides by the square root of 5 minus the square root of 3. And we get 10.3 centimeters from the 3 nanocoulomb charge. Now we have to get the coordinates of the point. X is 10.3, so the x coordinate is 12.3. And don't forget the y coordinate. It's plus 1 centimeter. The point at which the electric field is 0 is 12.3 centimeters in the x direction, 1 centimeter in the y direction. It is left as an exercise to the student to confirm that that is indeed the case. That's problem 3 on exam 2 in module 1.